Welcome everyone. Thanks for coming to the MUMS and LunchMaths Seminar. As you noticed, we will be recording this, and then with the permission from our speaker, we will also upload it to YouTube. This is Sharon from MelbUniMaths&Stats Society, which is known as MUMS. This year, we are teamed up with LunchMaths from Monash University, and we are planning to run a talk every second teaching week, alternating between speakers from Melbourne and Monash. This week, we're excited to have Dr. Volker Schlue from Melbourne University, who has very broad interests in physical sciences and mathematics focused on geometric analysis. Today, he will be presenting to us about black holes and expanding universe, a mathematical journey, which will be guided by his own research interests in general relativity theory. In this talk, we will be exploring the simplest model of black holes in the expanding universe and discuss some of the mathematical questions related to their dynamical stability. There will be also time for questions at the end of the presentation, and that will not be recorded, so feel free to ask. With that, let's welcome Dr. Volker Schlue, and I will stop sharing and hand over to him.
Thanks, Sharon. Thanks so much for the introduction. I am happy to see so many of you here. I also encourage you to turn on your videos if you have a chance. It gives me a chance to see how much or what the response is to what I'm talking about. And please feel free to ask questions as we go along. Let me see if that works, and I will share my screen. Where I now hope you can see some of my slides. The topic of this talk is black holes and the expanding universe, and obviously that's a very big topic, and there is a lot to be said about it, and many people are working on it and have thought about it, and each of them will have a different view on this. I'm gonna restrict myself to sort of a selection of topics that I've found have some relation to my own interest, and since I'm in mathematics, the topics that I've chosen and the way I talk about it is of a more mathematical nature. But I say this, and then maybe you will find exactly the opposite, because I've decided to take as a starting point into this journey the 1917 paper of Einstein, which is called Cosmological Considerations in General Relativity. And I've chosen this paper as a starting point because it marks, it's in this paper that cosmology becomes a mathematical theory. So I'll come back to it in a moment, but what I mean by that is, so if I found here a couple of, one is a drawing of Kepler, and the other is of Descartes. There are, of course, there have been, if you want, mathematical theories of the universe in the large before, here in this lower picture of let me see if that works, of Descartes. There you see sort of a graphical depiction of his ideas of vortices that are found throughout space, and he had ideas about the dynamical universe. And up here you see sort of ideas of the universe in the large, which involves all sorts of geometric shapes, in particular the Platonic solids. And you could say, well, these are mathematical theories. But what I'm trying to emphasize, as has happened in this paper, is a very different mathematical theory. What has happened here is that Einstein has proposed not a mathematical description of the universe, but he has presented a mathematical theory that predicts the shape of the universe and can make assertions about what the universe and the large should look like. And if you believe the underlying theory, then you have to live with its consequences. And what I'm going to talk about is some of the consequences that he and others have found. But I also use it as a starting point in saying a few words about what general relativity really is. And you see here in this paper, even though it's in German, you will recognize the words Newton. You will recognize Poisson's equation, and these are equations which so his starting point were the Newtonian theory of gravity, because you see, the Newtonian theory of gravity describes the world incredibly well. I mean, the Newtonian theory of gravity, describes, to a high degree of accuracy, planetary motion extremely well, and almost every everyday phenomena that involves gravitation is incredibly well described by Newton's theory. So it's not that Newton's theory is wrong. And in a lot of situations, it describes nature extremely well. So whatever general relativity is, it has to, at least in some situations, reproduce the Newtonian predictions. And that's why his theory is in particular his equations, the so-called Einstein equations, bear some resemblance and were inspired by Newton's equations. And I'm going to start out explaining this a little bit, and what led him to the introduction of the so-called cosmological constant, which plays an important role in the discovery of the expanding universe. So let's review for a moment what Newton's theory is. And so in Newton's theory of gravity, Newton tells us two things, so or maybe more. So in the first place, the whole theory plays out in Euclidean space. Space is three-dimensional, governed by Euclidean geometry, and it's a theory of gravity in the sense that it will tell us, given a certain mass configuration, it will tell us how particles, like this one here, will move in the gravitational field of that mass configuration. So more precisely, let's say you're given some function on Euclidean space which describes the density of mass. Then what Newton's theory will tell us is, if you then consider a test particle or a particle very far, at some position in space, moving with which has a certain velocity at a point, it will tell us the trajectory of this particle in the gravitational field exerted by this mass configuration, right? And so let's look a little bit how this is done. So what Newton tells us is that given that mass configuration, you first have to solve a partial differential equation. And what you see here is So this is something that you will all understand. So the Laplacian here, if you are on R3, is the sum of the second derivatives and so it is an equation. It's a partial differential equation for the so-called Newtonian potential, and he tells us solve it with certain boundary conditions, that the Newtonian potential should go to 0 at infinity. And if you have done that, then you can compute at any point in space the gravitational force that's exerted by that mass configuration by simply computing the gradient of that function. And then he tells us that that's his famous second law, is once you have computed that, you have to solve, you can solve an ordinary differential equation to get the trajectory. So now knowing the gradient of the gravitational potential, the force field, you now write down the equations of motions, which is an ordinary differential equation, and solving this ordinary differential equations with initial values, the initial position, and the velocity, you will get the trajectory, right? Okay, now there are a few reasons why I recall this. One is that we'll see how Einstein altered this law here when it comes to the description of the universe and the large. But there is another the reason that I'm bringing this up here is that you see, in Newton's description, there are, in fact, conceptually two different kind of masses that appear here. One is this mass, if you want, the passive gravitational mass, which appears here once you've computed the potential. It tells you the force that's acting on a particle that appears here on the right-hand side. On the left-hand side is the mass that appears in Newton's second law, which holds for any force acting on the body. And that is the inertial mass. Now, the reason that it's not usually not distinguished between these two masses is that, well, the two masses are the same. And so that means that from this equation, the two masses cancel, and that tells you that no matter what the mass of a body is, it will be accelerated in exactly the same way. All masses are accelerated in exactly the same way in a given gravitational field, and that is sort of the classic observation that if there are no other forces acting on you, if you're in vacuum, if you're on the moon, the elephant and the feather will fall to the ground in exactly the same way. And it's this observation that led Einstein initially led Einstein to general relativity, meaning it led him to realizing that general relativity is a theory of gravitation. So I will not have a chance here to explain this in much more detail, but I just want to maybe say that this observation that the gravitational mass and the inertial mass are the same, and that as a result all masses are accelerated in a given field in exactly the same way, that's also known as the equivalence principle. And this is a bit of a random example here, but it's what you see here is a drop tower, and that's just an example that I remember from my own undergraduate days. Here, this drop tower is used for lots of experiments, but in particular, it was used maybe in the 90s to give another sort of verification of the equivalence principle. So the idea is that, you know, if you drop, if you have a little laboratory in this tower that falls in that tower, and if you are sitting in that, little laboratory and it's freely falling, all the objects in there will be accelerated in exactly the same way. So if you're sitting in that laboratory, you have no chance of distinguishing, you know, between being at rest and freely falling. And you know, if you understand this, so, and you know, in the experiments that were done in this drop tower, it was used to verify, if you want, this identity here, or the equivalence principle to higher and higher accuracies. But the point is, in relation to general relativity, the point is that if you think of what relativity, in particular did, it told us about all the frames of reference which are equivalent from the point of view of describing physical phenomena. If you are in a moving train or on a stationary train, the physical laws that you observe are the same, and relativity tells us a way of translating the laws of physics from one frame to the other. What this equivalence principle forces us to is that also a freely falling laboratory is equivalent to one which is not falling at all. And so what that means is that whatever laws in physics you're describing, the underlying theory of general relativity has to include gravitation. So this was my attempt at telling you how what the equivalence principle has to do with general relativity. If you want to know more about it, there are lots, of course, various sources, but I encourage you, for example, to look at my lecture notes, where some of this is described, that you can find on my website. So, but back to the 1917 paper. So what Einstein had, I haven't told you yet what the equations were that he found, but he had developed a theory that would describe situations similar to these ones here, of isolated gravitational systems. What he became interested in this paper is, what does the theory tell us for the universe in the large? And if you for a moment think about the equations, Newton's equations that are sort of an anchor point for his theory, let's consider for the moment the situation that you would be in to describe the universe in the large. The density, the mass density would not be compactly supported at all. In fact, if you look into the sky on a good night with clear skies, you will see that the stars are pretty much evenly distributed. There are no big clusters, or, you know, of course there are some, but roughly speaking, it looks like the stars are evenly distributed. And that's what you see here is what I found here is sort of one of the earliest references of Herschel, which was sort of the earliest maps of the sky, and this sort of essentially from that time on until the time that the paper was written, the assumption that the matter is evenly distributed throughout the universe seemed perfectly reasonable. So if you take as a starting point, let's take the mass density to be a constant, right? This is a constant. And you look at Newton's equation, then you see that remember there were the boundary conditions that phi should go to infinity, that phi, the potential should go to 0 as you're going to infinity. You see that this equation is inconsistent with this boundary condition. In particular, moreover, or he put even more easily, if you say that if matter is evenly distributed across the universe, then there should really be also the forces should cancel each other all out. There shouldn't be any force acting on anything because it's all evenly distributed. So therefore, the potential should be a constant. But the potential being a constant is inconsistent with this equation. You have 0 on the left and something else on the right. So Einstein made a bold move. He said, maybe the correct, the equations, sort of Newton's equations to describe a cosmological, to describe a situation of cosmological scale, the equation should maybe be a different one. And he, in a quite ad hoc manner, introduced an additional term into the equation, which guided him, where here this lambda is a positive constant called the cosmological constant. And what you see then, of course, then things are perfectly fine. Then, phi being a constant, it would be a solution to this equation, and you would find that okay, it is a particular constant like this, and he was happy with that, and then set out to introduce this corresponding term here into his field equations, and that was what happened in this paper. And as soon as he did this, he then started to look for solutions in the same way that I looked here for a solution to this equation, right? And what he found was quite drastically different from what anybody had expected. What he found is that a solution of his equation, which is found under the sort of in the analogous situation as to the one that I'm describing here, namely a constant density of matter evenly distributed through space. He found as a solution, and I'll say what that means in a moment. You should, the solution in general relativity is the space-time itself, right? Here it was the unknown was the gravitational potential. I'll explain in general relativity, the unknown is space-time, the arena in which things play out itself. And what he found was the first model of a spatially closed universe. And what happened is that in this universe, space is not Euclidean at all. It is not R3, but it is S3. And so that means closed in particular, and no matter what direction you go, if you keep going for a long time, you will come back to where you started. And here you see, okay, that here what you see here is sort of a typical depiction of a so-called space-time. In relativity, we typically draw the time in the vertical direction and space in the horizontal direction. Space here is, but we can only draw on a piece of paper. But what we're trying to depict is 4-dimensional, so we are suppressing 2 dimensions in the spatial direction, right? So what you're hearing, this circle here, what this circle is meant to represent is a 3-dimensional sphere. And upwards here, you have time. So as time goes on, at any moment in time, space is a 3-dimensional sphere. In particular, that space here, that space-time is what we call static. It is independent of time, right? And that's what he set out to find, sort of an equilibrium configuration of space-time. And once he found this, he was quite happy with this. He didn't set out to find, and that's what I meant to describe initially. It wasn't initially his idea to say, oh, maybe space is not R3, but more like spherical geometry. No, no, no. It came from the equations that we wrote down. It's a prediction of the Einstein equation. It's a solution to the equations, and he was quite happy about that. Now, and obviously, it had a huge influence at the time. And what I want to say a little bit more here is about, so I already said that, so in some sense, I already said that the unknown is space-time. But now what I've drawn here is, if you want, the topology of that. I've told you roughly what, you know, what the space-time looks like, but what is more specifically the unknown in general relativity as the gravitational potential was the unknown in Newton's theory. The unknown in relativity is really the metric. Now, what you just roughly speaking, I already said in this picture here that the spatial geometry is that of a sphere, and if you describe, let's say, in a simpler situation, let's talk for a moment about the difference between Euclidean space and the sphere. You find that there's not just properties that, you know, let's say, like a property that the space is closed, that, as I said about the sphere, then whatever direction you go, you come back to it. No, 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 there are like significant differences when you talk about the geometry in these spaces, right? So for example, on a sphere, if you look at the triangles in a sphere, the angles will not add up to 180 degrees. And so, and this would have quite severe, you know, would have real consequences if one measured a triangle over very, very large distances in a universe like this. Euclidean geometry would not apply. And the way that this is the way that this is captured here, so what I mean by metric, a metric is well, specifically a bilinear form that allows you to do a couple of things. It allows you to measure angles. It allows you to compute the length of curves, and it allows you in this case to compute the areas. And so all the geometrical information is contained in the metric, and that is what is the unknown in general relativity. Okay, now even though Einstein was now happy with this prediction that his new theory gave, he was not quite prepared for what would come next. And what came next is that de Sitter found a different solution to the equations, and that's what I meant. What was postulated were the equations, not its predictions. So what de Sitter then looked at is a little bizarre, because as I said, so in this situation, there was actually some matter in the same way that there was an evenly distributed matter configuration in this setting here. What de Sitter looked at was, he looked at for a solution of these equations, which are now Einstein's equations, and you should really think of this. So what the left-hand side here is what the left-hand side here is a so-called Richie curvature, and it's a certain notion of curvature. But the way you should think about this, or you could think about it, just is that as this equation remember that that the Newtonian equation by which this was inspired by is this one. So you can think of this expression as some partial differential equation of second order for the unknown, which is now a metric. And what de Sitter looked at was the situation where there was no matter present whatsoever. The matter of density was the density of matter was zero, and he found a non-trivial solution of what should really be a trivial solution. So he's looking for the geometry of space-time in the absence of any matter. And what he's finding is more like a solution like this. It looks, the topology of that space is very much like the Einstein static universe, except that these spheres seem to get bigger and bigger and bigger as time goes on. Now, I will explain, this is not at all how, this is not at all what he realized, or Einstein, or anybody at that time. You know, nobody saw the Sitter solution in the way that I'm drawing here, but and I'll explain in a moment how they thought about it. But essentially, as soon as Einstein realized that this is what's going on, he was prepared to forget about the cosmological constant immediately. And it's sort of a classical story. Here is, don't know if I find the relevant part, but there is sort of a proof of this in a postcard that Einstein wrote, where he said, well, if this is what the cosmological constant entails, gone with it. Let's forget about it altogether. But at this point, nobody was ready to forget about it anymore. In fact, now it's one of the sort of foundations of modern cosmology. Okay, let me say a little bit more about what's so disheartening about de Sitter's solution is that so de Sitter's solution from a modern point of view can be described extremely easily. All that it is you take you take R5, and you consider the one-sheeted hyperboloid in that space, and you take as its metric the metric that is so-called induced from the ambient Minkowski space. So you equip not the five-dimensional Euclidean space, not with the Euclidean metric, but what's called the Minkowski metric, and you restrict the metric to it, and what you simply find is de Sitter's solution. And as I tried to depict earlier, this is a very similar situation. It's spatially closed. Time here is upwards. And these spheres now get bigger and bigger and bigger. The space is expanding. What's even more concerning in that situation is that, so in general relativity, once you know the geometry, or once you know the space-time in the large, you can say how particles move. So think about the initial situation where I said you compute the gravitational field that's exerted by a mass configuration, and then you have to solve an ODE you have to solve Newton's second law to get the trajectory. Here, in general relativity, once you have the geometry of space-time, the trajectories of freely falling particles are so-called time-like geodesics. So let's think, I will not go into it much more, but essentially already in what's called Riemannian geometry, if you're given 2 points and you want to find the curve with the smallest arc length, that is called a geodesic. So I said you can talk about the length of the curve, if you take 2 points and you look at all the possible curves connecting 2 points, the one with the smallest length, that's a geodesic. And you can talk about a similar notion in Lorentzian geometry, and these will be the freely falling bodies. Now, believe me here that the freely falling particles in this space, they look like this. They're simply the intersections, if you want, of the hyperboloid with planes through the central axis. And what you see is, you should think of these 2 points, these 2 observers here. There are 2 points which are initially at a certain distance, and they don't move. They do not move, right? They have, if you want, 0 velocity. But nonetheless, as time goes by, the distance between these two observers becomes larger and larger and larger, and for no apparent reason. And that is what what concerned Einstein so much. That is against all the principles of the time, that in a universe devoid of matter, two particles should for no reason whatsoever be accelerated away from each other. That seemed enough of a reason to think that the whole idea of the cosmological constant was a huge mistake. And then certainly he didn't believe that these solutions had any physical significance. What I want to say here briefly is that the way I'm describing the Sitter solution was not at all how it was found initially. Like Einstein for his, static universe, the idea of having a static universe was very central to their thought. So what people were looking for were static solutions, and de Sitter actually did find a metric which was static, meaning independent of time. You don't see any t in those metric coefficients here. And what he, however, found was, if you want, what this geometry looks like when you restrict it to a certain patch. So if one looks at a small patch of this big space-time, you can express the metric in this way. And it was not realized at all what the global geometry of this space looks like. And there's, in some sense, no reason to go back to these old confusions, except that it highlights a very important fact about the geometry of these spaces, which is that here, what you see here, what this region is, that is to the past of these 2 lines. What you see here is, so if you think of this guy as an observer, what you see here is the past of that observer intersected with its future. So any point in here is one that could have been influenced by him at some point, or that could be seen by him at a later point. So what you see here is, in particular, if you have another observer, one of his friends a little bit further away, who is moving on one of these time-like curves, on these curves upwards, at some point he will cross this line here, which means that as soon as he has crossed this line, he will not be able to communicate with the observer anymore. So what is going on here is, so I said that an observer, a freely falling particle maybe looks like this. And the significance of these lines here of 45 degrees is that, so if he were, this is an observer at rest, this is one that is trying to get to his friend gamma, and if he decided he is too slow and he wants to send a signal, a light signal, then it would travel on a line like this. And what you see from this picture here is that that there is a point, once he passes this, he will not be able to communicate with gamma anymore. And that is one of the basic properties of an expanding universe. We will, if we are in an expanding universe, we will not be able to observe all events that have happened, even if we lived forever. There are some which will be inaccessible to us. The events are causally disconnected. And so what this surface of significance here is called is a so-called cosmological horizon of that observer. It's his horizon. Anything that's beyond it, he will not be able to see. So so Einstein abandoned his static universe, but he did not do it. He did not do it on the grounds of increasing observational evidence, which supported the idea that that maybe we are in an expanding universe, or maybe which or maybe all the galaxies nearby which we see are receding from us. So I will explain that observational evidence in a moment, which was accumulating at that time, which told us that it was observed that if you're looking out into the sky, all the nearby galaxies, they seem to be moving away from us, which is a picture which is perfectly compatible with, say, this one. But this was not at all what convinced Einstein. What convinced Einstein, it seems, and that's something that you can read about a lot in this book here, from which I've taken some inspiration in preparing this talk, is a conversation that Einstein had with Eddington, not at all about the observational evidence of the time, but about the fact that his universe is unstable. So what happened was that this gentleman here, Lemaitre, had found a family of solutions which included Einstein's solutions. And Einstein had seen those solutions, but like the Sitter solutions, he had dismissed them as entirely unphysical. And he was not ready to give up his static universe. But what Eddington observed here was that, you see, in Einstein's universe, you, like in the same way in the Newtonian analog, you find here a relation between the radius, the cosmological constant, and the density. Now, if the density happens to be slightly different from what it's supposed to be according to this model, then Eddington simply observed that using Lemaitre's solutions, he observed that Einstein's universe would be unstable. The space would immediately either start contracting or expanding, and it's this insight that allowed Einstein, or that apparently shifted Einstein's thought. And I find this quite interesting, because it's really this notion that a space-time only has, a space-time as a prediction of general relativity only has physical significance if it is stable in a suitable sense. And it's this idea that has sort of guided modern research in the field. And I jump here forward a little bit to a paper that was written in the late 80s, which established the stability of d zeta. And when I say stability, there is quite a shift here in how we think about general relativity. Einstein believed in particular in a static universe because he, to him, the idea of a dynamical universe was not something that he embraced. And it wasn't clear in his mind that this is what his theory holds. So what I'm talking about here is that, maybe this comes on the next slide, is that if you look at Einstein's equations, and now this is now back in the setting of a vanishing cosmological constant, I explained that his equations were sort of written down in analogy to Newton's equation in this case, which are elliptic, which are which you can solve. Which, as I said, if you have a right-hand side and you have some boundary conditions, then they tell you you can write down a solution of this equation instantly. But what transpires, and what wasn't so clear initially, that this equation that he wrote down is really much more like the wave equation, because the metric is Lorentzian. And as soon as you have, maybe a little bit of a word here. So as I already wrote down what the Laplacian is, here what this ominous symbol denotes would be if you were on R3 plus 1 and you had coordinates t and x, what this would denote is more something like this. And that is a wave equation, and it gives rise to a very, very different problem. It gives rise to an initial value problem. It gives rise to saying these solutions of these equations are found by knowing, let's say, phi at a certain time. And then what this equation tells me is how this configuration evolves in time. And this is precisely what I'm trying to say here. If you want, the stability of de Sitter establishes that if space at a certain time is not exactly like a round three-dimensional sphere, but it's a little bit wobbled, it has like a couple of dents here and there, then Einstein's equations will tell us how the space evolves in time. And what one finds is that nothing too drastic happens. The spheres will still be expanding, and they will always be close to the round spheres. And in particular, these spaces will be what's called will be complete, will be called geodesically complete. What you have here is maybe an encouragement for all students. That's this. What you see here is a paper which was written in the 50s, which happened to be Yvonne Choquet-Bruhat's thesis. So here you see her. It's this photo I took at her 90th birthday conference. And what you see on the left is essentially her thesis, much earlier in the 50s, which set off the field in viewing Einstein's equations as a hyperbolic partial differential equation, a hyperbolic nonlinear system of partial differential equations, which in principal type are more like a wave equation than Poisson's equation. And the reason that this was non-trivial to observe or to see for Einstein from the beginning was that the Einstein equations can be written down in many, many different ways. Depending on what coordinates that you choose, they look very different. But if you choose coordinates which themselves satisfy the wave equations, which themselves satisfy the wave equation, then the Einstein equations take the form of a hyperbolic system of wave equations. If you want to know more about it, you can also look at my my lecture notes, which describes the general formulation of the dynamical formulation of relativity. Now, I want to jump forward very briefly. There is, of course, what was done in this thesis was it was understood that this problem, the dynamical formulation of general relativity, is well posed, but it left open how these solutions behaved after a very long time, which was only solved in the 90s. So under the title of the stability of the Minkowski spacetime, which is sort of the simplest space-time and the arena of special relativity. And I will not go into that at all, except by saying that it was found that these solutions are free of black holes and singularities, which I haven't talked about at all, and which I want to get to next. However, looking at the time, I'm seeing that it is 5 to 1, and I've already used up a lot of my time, although in reality, in view of what I wanted to say, I'm only halfway through. So I don't want to subject anybody to more of this unless you would like me to. So maybe can I hear from you whether I should stop here or whether I should continue?
Yeah, maybe reaction to the thumb if you would like.
Sorry?
There's a reaction. You can raise a thumb if you would like to hear about more. Yeah, I see more people in the chat said more, please. Yeah.
Okay. So I will not be offended if you have to leave, but I will maybe then indeed say a few more words about the role of black holes in this whole topic, which is what I promised I would say a few words about. And maybe I will say this, I will try to keep it relatively brief. But what I want to get at is what I want to describe is not just the model of an expanding universe that I have sort of presented to you now, but I want to describe to you the model of a black hole in an expanding universe. And roughly speaking, so before the 1917 paper, Einstein set out originally in his 1915 paper, general relativity in its final form without a cosmological constant. And essentially, very, very shortly afterwards, Schwarzschild discovered a solution which the story of which is in fact, the story of that is not very different from the story of de Sitter finding his solution in the sense of the similar confusions arose very early on, and it wasn't fully realized what Schwarzschild had discovered. What Schwarzschild was looking at was very much, if you think about the Newtonian situation, let's say you try to solve the Newtonian situation with a spherically symmetric mass configuration. And you find a spherically symmetric gravitational potential. He set out to do the same thing in general relativity. He said, okay, well, if there's a new theory of gravity, let's see what the solutions of what this theory predicts for a spherically symmetric configuration. In fact, in his title is sort of the gravitational field of a mass point. And what he found was a geometry, a space-time that indeed describes the geometry of space and time and the gravitational field of a spherically symmetric object. But what he had also found, and that wasn't realized at that time, he in fact had found a black hole solution. And so I will, instead of trying to now explain Schwarzschild's solution separately, I will directly try to explain the so-called Schwarzschild-de Sitter solution, which is the same, which is sort of a combination between Schwarzschild's solution and de Sitter's solution, and it is the model of a black hole in an expanding universe. The irony is on this that even though we say it's a Schwarzschild-de Sitter spacetime, neither Schwarzschild nor de Sitter discovered it. In fact, it was at this independently Hermann Weyl and Friedrich Kottler who discovered that spacetime. But it is somewhat easier to say what a black hole solution is by referring directly to what I've already told you about de Sitter. So I've highlighted that de Sitter has a cosmological horizon. Each observer has a horizon for when it's such that when it's crossed by another observer, that observer will not be able to communicate with him anymore. Now, how you can think about the Schwarzschild-de Sitter solution is you replace that observer, gamma, here, by a black hole. And what happens as a result of it is that there will be an additional horizon, the so-called event horizon, which has a different meaning, whose significance is once an observer crosses that horizon, he will not be able to communicate anymore with the outside. But the concept of the horizon is very similar. So let me say it here in these schematic terms. You have up here a so-called Penrose diagram of de Sitter, where you've seen here now it's a bit simplified. I'm not going to go into how this is related, but you see here this orange line was our S3 from previously, and we had seen here one observer, of which I said he has a cosmological horizon. What's new is in the so-called Schwarzschild-de Sitter solution is that there is now no central line anymore of the observer. There is a black hole, and that black hole has an event horizon, which now means you're arriving in a space-time where, as I said, the observer can either cross the cosmological horizon, in which case he will not be able to, well, either encounter the black hole or send a signal into the black hole, or he will cross the event horizon, in which case he has no chance anymore of either leaving the black hole or communicating with an observer that has remained outside. And I guess I want to say here a few more words about what is happening when you cross that event horizon, because also here, as the observer that crosses the cosmological horizon doesn't know that he's crossing the cosmological horizon. There's nothing special of, he doesn't encounter any local difference in the space through which he's traveling. In the same way that if an observer crossed the event horizon, he would not know that he is crossing the event horizon of the black hole, and from then on unable to communicate with the exterior. What is different is though how he is viewed from the outside. So what I want to explain here is the situation of you have here sort of the depiction of the event horizon and an observer that decides to enter the black hole, and an observer that safely stays outside the black hole for all time. Then what you see here is that if that observer who goes into the black hole communicated with the observer who stays out by sending him steady signals at equal intervals in time, let's say every second he sends a signal, then for him, there are only finitely many signals that he sends before he crosses the horizon. But for the outside observer who lives, in this case, let's say, for all time, these signals will become more and more and more spaced out, because in reality, so the length of this curve is his lifetime. And since he doesn't, the length of time corresponds to the time that passes. And as for an observer that lives forever, the length of this curve is infinite. And so the distance, or the intervals in which these signals arrive, will become longer and longer and longer, meaning the frequency will be lower and lower, meaning the wavelength will be larger and larger. And that means that really the light that is so if an object fell into the black hole, it would first of all take an infinite amount of time from the point of view of the observer, and the light that he's seeing would be more and more and more shifted to the red. And that is, let me just, we all have heard about this. Last year there was, from the Event Horizon Telescope, there was the first direct observation of a black hole. And what you see in particular here is that the center is black. There is no light arriving directly from the black hole. As you would see here, as you're coming closer and closer to the horizon, that light would be shifted into the red more and more until it fades out and it becomes invisible. And in this picture, actually, there is much more going on, and I'm not really a specialist on this. But another phenomenon that plays a big role here is that the so-called Photon Sphere. So if you imagine that the event horizon corresponds to some sphere that surrounds the black hole. If you are further outside from the black hole, you don't just have the option of sending light straight into it or away from it. You could also send light parallel to it, so in this direction. And what one finds in these geometries is that the light, as it's sort of depicted here, becomes trapped. The light can circle. It can circle around the black hole forever. And these so-called and it could also circle around for a while before it escapes, or it could circle around for a while before it goes in. And so there are these so-called gravitational lensing effects that play a big role in how a black hole looks like for an external observer. Okay, so just very briefly on this, maybe just a word on what happens to the observer once he crosses that horizon. He's now in a situation where where whatever he does, he will not be able to escape. And in particular, what happens here is that all the light that he sends out doesn't escape. And one can depict that a little bit like this. So what I've tried to draw here is the situation in flat space. So let's say here you have three-dimensional space, and you think of a sphere of a certain radius. And so more practically speaking, think of maybe a glass ball, and the glass, and let's say you have a glass ball which is covered in light bulbs, and at some point you decide to turn on all the light bulbs, then what is going to happen is that there will be light traveling inwards and light traveling outwards, and that's depicted with these two wavefronts. So this is the light that's going in, forming a wavefront that which is again a sphere, which is now of smaller radius, and there is a wavefront going out, forming a sphere of bigger radius, right? What would happen on the horizon is that the outgoing, so if this was the horizon, what would happen is that the outgoing wavefront the outgoing wavefront has a fixed radius. It doesn't go, the wavefront doesn't escape to bigger and bigger radii. And if you are inside the black hole, both wavefronts would be going to smaller radii. Both the outgoing and the ingoing one would really form wavefronts which are contracting. And it's this notion of what's called a trapped sphere that Roger Penrose has identified and come up with, and realized that this is the relevant notion in the study of the dynamics of the interior of the black hole, if you like. What he has realized is that, and this is the paper that was awarded a Nobel Prize, what he has realized is that if you have a space-time which contains a trapped contains a trapped sphere and satisfies a number of other conditions, then this space-time cannot be geodesically complete. The space-time cannot be complete. And some of the motivation of this is that what was found for the so-called Schwarzschild solution, what's the case in Schwarzschild de Sitter, is that the fate of an observer is quite drastic. So not only can he not escape, but actually he will eventually hit a singularity at the center, and it wasn't at all clear, or it was a big question at the time, whether this specific singularity that appears here is a consequence of the high degrees of symmetries of the solutions that were considered, or whether this is a general phenomena. And what Penrose did is he found that the presence of a trapped surface itself, together with the Einstein equations, implies that these spacetimes will always be incomplete. Now, what the nature of the singularity really is inside a black hole under different situations, that is a topic of contemporary mathematics, and one could easily talk, have a separate talk about this. But in any case, what Penrose realized that this is not at all a consequence just of the symmetries in the problem. Maybe to come back now quickly, as I said, I'm emphasizing that both Schwarzschild de Sitter, both in the expanding universe we have a horizon, and also in the black hole spacetime we have an event horizon. I've explained the phenomena of the Redshift effect that's observed in the discovery, that's observed when we talk about the propagation of light coming from a black hole. A very similar thing is now happening due to the presence of a cosmological horizon in an expanding spacetime, which is a cosmological redshift. Also here, in the Sitter, if you like, because the rate of clocks is different here than it is here, you would, if an observer sent a signal to another observer, the way it's depicted here, the signals that he is sending would be increasingly shifted to the red. And here now, in the sitter, there is absolutely nothing special about this particular observer, right? I mean, any observer has its own cosmological horizon. So no matter where you are, the signals that are arriving to you are shifted to the red. And this is precisely what had been observed. It was certainly not with this picture in mind that they were explained, but quite early on, I think Fraunhofer had understood what the spectrum is, what the solar spectrum is, and you could then so that essentially tells you, for example, what elements are present in the solar spectrum, and you could point the telescope at nearby galaxies, at Andromeda and others which were available, and you could measure the spectra, and you could see that these lines were slightly shifted to the red. People did not, think or were concerned about the origin of that redshift, but they knew about the Doppler effect. They knew that if a signal is shifted to the red, then it must mean that these objects that are sending these signals to us are moving away from us. And these were first observed by Schleifer, who tabled all the nebula together with their velocities. And this is a reprint here from the table was reprinted in Eddington's book of general relativity. And what you see is that essentially most galaxies are redshifted, are moving away from us. So I think I'm gonna just finish by saying that one of the reasons that I'm talking about this is because this, on one hand, this cosmological redshift is certainly what convinced the scientific community at the time that these models are physically relevant, that we are living in a universe where objects are accelerated away from each other. And but what I want to come back to for just a moment is that, as I've said, I've emphasized that this idea of space-time being physically relevant only if it's stable has sort of guided mathematical research in the past couple of decades in particular. And a problem that I'm interested in is the stability of the Schwarzschild de Sitter solution. And in one of the early papers that I wrote in my thesis, I had looked at the sort of simplest model problem, which just looks at the wave equation on the Schwarzschild de Sitter space-time. And what I'd found is that this global redshift that I'm sort of schematically illustrating here has a manifestation as a so-called energy estimate, which is relevant for the prevalent stability mechanism for these space-times. And since then, I've worked quite a lot on understanding the stability of these solutions as solutions to the Einstein equations. And if you are interested in what the status of all of this is, and you're welcome to look at an online talk that I gave at a conference recently, which you now are perfectly equipped to watch. Okay, I think I'm going to stop here. Thank you so much for giving me a few extra minutes. I'm looking forward to your questions, and thanks again for giving me the time.
Thank you so much, Volker. And thank you everyone for staying here. And that's a really wonderful talk. And I really like your handwriting slides.
Thank you. Yeah, I've never used that app before, but for a talk, but it works quite nicely.
Oh, wow. Thank you. And I'll stop recording now.